published the origin.
Thank you, Dr. Pura. Good morning, everyone. I'm going to talk about the extended wavelength infrared detectors and split of band infrared detectors. This extended wavelength mechanism is newly observed phenomenon in our group while studying these split of band infrared detectors. First, I'll show some examples of applications of infrared detector systems, and then I'll present one simple device structure for mid-infrared detection using P-gas all-gas system, which will be used as a reference detector to compare with extended wavelength photodetectors, which have different device parameter variations. And also, I'll show dark current characteristics of the extended wavelength infrared detectors with reference to the reference detector. And then my continued work on split of band detector for 3 to 5 micron detection, the ongoing work. So the infrared radiation is a portion of the electromagnetic spectrum that is beyond the red color invisible. And in terms of frequency, it is mostly in terahertz. So some portion of the infrared is also called terahertz. 30 micron wavelength is 1 terahertz. And this radiation is emitted by all kind of objects in the temperature range of few kelvins to a few thousand kelvins. So infrared imaging is basically the temperature mapping of those objects emitting infrared radiation. So it has a lot of interesting applications in security and military applications, defense, firefighters use infrared imaging system because it's very useful. They can see through the smoke. However, using infrared imaging system, they can see through the smoke, so that it makes their job easier. So there is, news coming out recently in California campfire that California Highway Patrol uses infrared cameras to track fire and to track people in vehicles in need of help. Recently, there is growing interest in the application of terahertz imaging systems in security screening, like in airports. Another interesting application is in astronomy. This is an infrared image of center of Milky Way galaxy, and they call it downtown Milky Way because there are cluster of stars crowded near the center, which would be difficult to see invisible, but infrared it is clearly seen, and this kind of application is interesting. So the detectors we are studying are photon detectors. They are faster and more efficient than the thermal detectors, and the operation of these detectors can be photovoltaic if no external bias voltage is applied, or photoconductive if external bias voltage is applied. And we are looking at two main characteristics of photon detectors: noise and signal. Both of them are critically dependent on the energy gap or minimum gap energy gap of photodetection. Both dark current and photocurrent photoresponse, the wavelength threshold of the photoresponse is determined by this minimum energy, which also controls the dark current. So the idea around what extended wavelength mechanism is that this mechanism allows to overcome this fundamental limitation. We can get the photoresponse beyond the limitation of this delta. So that is the main idea around the extended wavelength mechanism. There are certain spectral bands in infrared that are more important than others. 3 to 5 is one band, and 8 to 15 is another one. And we are primarily interested in 3 to 5 band because US Army is interested in the detectors in this band, and we get support for our research from US Army. And we are using mostly semiconductors, 3 to 5, and gallium arsenide, aluminum gallium arsenide heterostructures, mostly because you see there is a very good lattice matching between these two material systems, and that is very important to make large scale focal plane arrays, large number of pixels. And also because we are also p-type, because the split of band energy gap is close to the mid-infrared range that we are looking for. This is a typical heterostructure band alignment: gallium arsenide, low energy band gap; aluminum gallium arsenide, high energy band gap. And we can change this offset by changing the aluminum fraction. So for the p-type, and highly doped, close to 10 to 19 per cubic centimeter or so, the formulable is in the valence band, and the difference between the formulable and barrier is controls the energy gap, and that controls the spectral photoresponse wavelength. And for the operation, we apply bias, and if there is infrared radiation incoming with infrared radiation of certain suitable energy, then that can be detected. It can be also operated without bias if the barrier is graded by changing the aluminum fraction from low value of X here to high value of X here. This can also operate at zero bias. So based on this kind of structures, p-type gas-all-gas system, first split of band detection was seen in 2006 in mid-infrared there, and after some device modification, there was room temperature operation also observed based on this kind of heterostructure in the split of band. Yes.
What is this bias?
We have these heterostructure layers, and above the active region and below the active region, we have highly doped contact regions, and we deposit metal contacts on those layers. And on those metal contacts, we do wire bonding. From them, we connect a bias voltage from batteries. So the performance actually depends, usually like less than 1 volt or more than 1 volt. If the device has very high resistance and very thick layer, then bias needs to go high, like even 5-10 volt range. But it really depends, and it's actually the field, means the bias divided by total thickness of the barrier. That is important, and the field is usually in the range of these devices in operating in mid-infrared. Fields are in the range of 100 kilovolts per centimeter or something like that. I'll show you later bias range for the operation as well in actual devices. So to improve the performance of these devices, a device modeling study was carried out, and in this study, and this type of structure was suggested with a barrier offset for the improved performance, improved collection, and graded barrier for improved injection for mid-infrared detection. But in this device, not only the mid-infrared, actually the photoresponse was observed much farther away than away from the mid-infrared. So that is beyond the limit of delta. Limit of delta is mostly here in the cellular region. However, the photoresponse actually is much farther up than that limit. So this is the extended wavelength photoresponse, and recently observed, published in 2014. So this kind of photoresponse, extended wavelength photoresponse, shows very interesting properties. For example, if we block high energy radiation around that region, actually that extended wavelength photoresponse disappears. So what we do is we put an optical filter which is transparent beyond certain wavelength, cotton wavelength, but shorter wavelengths are blocked. So you see the extended wavelength for response became weaker. With longer cotton filter, it becomes further weaker. With 4.5 micron, it is mostly gone. However, with an external source of infrared radiation falling onto the detector, that mechanism is recovered. That extended wavelength for response is recovered. So this means this so that there is some high energy infrared radiation that is necessary for this kind of mechanism. That was the finding. And based on the results, one possible mechanism was suggested, mechanism of this photo detection. And in this one, the high energy injected carriers from the bottom contact were supposed to redistribute their energy so that Fermi level is elevated, and now the infrared radiation with smaller energy can be detected. So that was the suggestion. And now from here, to get detectors, to be able to design detectors with more precision and a more higher performance, now we wanted to go further and parameters of the device, like this energy, this offset, and also the gradient, and see what happens. How can we come up with more controllable design for the detector? So I'm going to show that. Before that, I'm going to show a very simple structure without any offset that does not show extended wavelength photo response. So this is the structure that does not have any offset. So this detects based on the absorption in the split up band from heavy hole light hole band to, and also there is light. So the energy threshold of split of absorption is 0.34 electron volt, but because of high peak doping, Fermi level is in the valence band. So the absorption, actually peak absorption is in the energy slightly higher than this. So this energy corresponds to 3.5 micron or so. So this peak corresponds to 2.7 micron or so. So this is the schematic of heterostructure and corresponding band diagram. This is one of the mesas, 400 by 400, and there, the smallest mesa there is this 400 by 400. And to add to your question earlier, so we apply bias from these contacts. So these contacts are wire bonded to the mesa, and there are two. This is top contact. This is bottom contact, which is common for all different mesas, and we connect bias positive and negative terminal. So if the positive terminal is connected to the top contact, it is positive bias. If the positive is connected to the bottom contact, it is negative bias. Yes, and this top layer is partially etched to open optical for the optical illumination. Otherwise, most of the absorption will be on the top contact, so we will get photo response mostly from the middle active layer. So this is partially etched. So the total thickness growth is like, yeah. So here is just to show schematically. So the total thickness in the design is like 200 nanometer in this one, but it is partially etched, and after etching, like is like 20 or so left in the that layer. Yeah, surface area. Then now optical surface optical window becomes 260 by 260. It is slightly smaller now. And this is the darker end of the device. We expected the device to be perfectly symmetrical based on the design. The barriers were constant in profile. However, the growth probably was not like perfect. Because of that, we see very small asymmetry. Darker end is in the negative is slightly higher compared to the positive, and photo response also shows that. So if
Dilip,
yes.
can you explain
Sure.
the dark current?
Okay, so what we do is we mount the sample in a cold finger, which is enclosed by a metal shroud. So it is completely isolated from radiation from external environment, and that is cooled down to low temperature. And we measure the current, just the current. We apply bias and measure the current, like in a resistor. But the property of this is semiconductor. It is not just like a metal or other regular resistor. The resistance is dynamic. It changes with the bias applied. But it is just like measuring. In principle, it is like measuring the current in a resistor. But under dark current, there is no light illumination. Dark current, yes. So when there is light or infrared radiation, then that is not dark current. There will be that will be actually photocurrent. So the photo response. Not in this one because thermal mechanism is slightly different. There are different material. I mean, gallium arsenide is also shown to have thermal detection mechanism, but thermal detection mechanism is basically they are different. But in the type is the mechanism is bolometer type, which means with the incoming infrared radiation, the resistance of the device changes, and that gives a measure of change in the current. So that is slightly different way. In this one, actually, the carriers are photo excited to higher energy level, and collection of those carriers gives the external signal. But there is thermal mechanism too. In those, the photocarriers are not excited, but the resistance of the device changes with the radiation. So mostly vanadium dioxide or something, those kind of material are mostly bolometer type thermal detectors. And with if the barriers were perfectly symmetric, the probability of photo emission in that direction or that direction would be equal. So we would expect no photo response at zero bias, but there is. That means most probably there is a very small unintended gradient that comes because of the growth conditions, possibly. And like I said before, there is peak absorption at 2.7 micron or so. That is peak split of absorption. And there is also absorption, light hole labial absorption beyond 3.5 micron, which is the 3.5 micron is the limit of split of absorption. And in the negative, so the negative bias tries to drive the carriers in the opposite direction. So in small negative biases, the photo response becomes weaker compared to that of zero volt, because there is a cancellation because of the opposite direction of the photo current. Slightly increased bias, the photo response in the negative slightly increases. With further increase, it becomes stronger in the other direction. Now that we have photo response, we want to see what is the threshold energy or threshold wavelength. And we look at the quantum yield. This is experimental quantum yield, which is proportional to responsivity multiplied by the energy. And to find the threshold, we are interested in this region where there is a threshold. So we apply a fitting. The method is called temperature-dependent internal photoemission spectroscopy. So based on this fitting, and this energy is obtained as a fitting parameter of this fitted curve. And this is for zero bias. We have this for we can do it for all different biases. So there is another way to find out that delta under dark condition as well from the dark current. So dark current is proportional to this term, and if we plot natural log of the dark current divided by this temperature term versus inverse of temperature, then we get this kind of plots, and from the slope of these plots, we can get the activation energy under the dark condition. So these are the values. So we see In negative bias, there is some difference in high biases, again, probably because of that some unintended gradient that is there, small gradient. So in the next step, for the extended wavelength mechanism, our focus is photoresponse and photoresponse in the extended wavelength range. So we are going to use Dilip's method to find the threshold energy. So these triangles from the Dilip's method from the photoresponse, and this RNS means from the dark current. So these are the devices for extended wavelength mechanism. We have barrier offset. One device has a constant barrier, and other devices have graded barrier, and the barrier offset is changed in different devices by changing this aluminum fraction there, and also the gradient is also changed by changing this aluminum fraction x1 in the graded barrier. So here is the table showing the different values. So we have 3 devices with increasing barrier offset, SP1001, the result I showed you earlier. And in the next step, we studied this device with higher offset, and the results were encouraging. So we went further to increase the offset to this value. And also from this device, we also changed the gradient to these different values. So we have a set with 3 different offset values and 3 different gradient values. And LS1002, the device I showed you earlier, the reference device, does not have barrier offset, does not have gradient by design. And this device will have offset but no gradient, so this comparison between these 2 devices will show the effect of this offset. And from this device to this device, the comparison will show the effect of gradient. So these are the results. Without the offset, there is no extended mechanism. However, the device with constant barrier but with offset, there is extended wavelength mechanism, and with the gradient, that photoresponse becomes stronger. And overall shape in both cases appear to be the same, meaning the mechanism appears to be the same in both devices. The wavelength threshold, obviously the reference device has in mid-infrared. SP1001 has 50 micron or so, SP1007 56. So now from SP1007, from this device, now we are going to these other 2 devices. So 15SP3 first. These are the photo response results, and from this one to the next, JSU171, these are the photo response for these devices. Now we have 3 devices and the photo response. So by comparison of these 3 devices, we see that the strength of the photo response with increasing barrier offset, the photo response is also increasing like this. And looking at the wavelength threshold, the threshold, there is a small variation, but overall pattern, the mechanism of the photo response appears to be similar. In other words, so what we changed in these 3 devices is we changed the barrier offset from lowest offset to the highest offset. The change is 0.13 electron volt. The change in the threshold is 0.002 electron volt. We didn't see any proportional change in the threshold. So now the question is, what could be the mechanism? How we got more or less similar threshold while we change offset like this. So the Fermi level, the quasi-equilibrium Fermi level in all devices appears to be in the same level, and the label that does not change from device to device is again that peak split off transition level corresponding to 2.7 micron or so. So that this is the indication that the quasi equilibrium Fermi level is same in different devices, even though we change the parameters. So this is also more clear from this result at zero bias. So at zero bias, there is net carrier flow from the emitter towards the bottom contact, because the collection efficiency for the carriers moving from emitter to the bottom contact is higher compared to that in opposite direction. So there is no applied bias, no net carrier injection from the bottom contact, but we still see the extended mechanism. So again, so the possibility of quasi equilibrium Fermi level is in the same level as before, and that builds up because of the photoexcitation from the ground state to that peak split off level. And again, if you remember, when the filter was used to block the high energy light, the extended wavelength disappeared. So that is probably related to the blocking of the transition to this level, so that the extended wavelength was disappear. And so at zero bias, we saw this result, and the directional preference is also becomes clear when we apply small negative biases. So what happens is, with small negative bias, again the photoresponse is in opposite direction, so there is cancellation, and that becomes weaker now. And with further increase in negative bias, we see at this point, at this wavelength, it is completely cancelled. And in this range now, the photoresponse becomes stronger in the opposite direction. That's why we see the change in shape at 0 volt and at negative 0.2 volt. The shape appear to be similar, means that the current towards the bottom contact was dominant. Now the photocurrent is dominant in the opposite direction. So when there is no gradient or graded barrier there, so we barely see any photoresponse at 0 volt, but when we apply bias, that starts to show up. So based on these results, what we can say is the quasi-equilibrium Fermi level that is necessary for the extended wavelength mechanism appears to be more or less fixed from device to device, and it is basically depends on the material property or the energy bands like split up, and the buildup of quasi-equilibrium Fermi level for the extended wavelength mechanism. So these findings will be very helpful to go to the next step to design more efficient kind of detectors. I'll show that later, but before that, I want to show you the results from the variation of gradient. So far, I was showing the variation of offset. So this is the device that has higher gradient compared to the first 15S3, and that is another one, DSU 17.3. So the overall shape appears to be similar. By comparison of the photoresponse, the intensity appears to be slightly weaker with increasing gradient of the devices, but mechanism, because the overall spectra appear to be similar, so the overall mechanism appears to be same again. So wavelength threshold also changed slightly, but is still in the same similar region. So far, all the measurements were carried out at 5.3 for the extended wavelength mechanism, but our interest is to develop detectors that operate at high operating temperatures. Okay, wavelength mechanism is gone dramatically with the temperature. That is one question. Dramatically is the phonon population with the temperature, and for gallium arsenide, allophonon energy is 0.036 electron volt, and you see the occupation number from 5 Kelvin to 50 Kelvin or so, it changes by many orders of magnitude. That is one thing. But again, the question is, why is this related to the extended wavelength mechanism? So to find the connection, let's look at the physics of physical property of material studied by many people over many years. So when there are photoexcited carriers, they undergo energy relaxation process, and the dominant mechanism is allophonon emission. And when there is a high emission rate, the allophonon population will go out of equilibrium. When that is out of equilibrium, then further phonon emission is slowed down. And that is called phonon bottleneck effect. And when that happens, the photoexcited carriers in bulk material, the carrier lifetime is very short, in the order of 1 picosecond. However, in quantum wells where there is one-dimensional energy quantization, and when there is high energy, high carrier density, the carrier lifetime becomes longer, hundreds of picoseconds. And in quantum dots, the energy confinement is in all three dimensions. So there is high energy mismatch between the phonon energies and the quantum dot energies. So carrier lifetime is much longer, in nanoseconds. And also not just in semiconductors, I think this is different material, kind of salt or something, lead hydride perovskites. And people are studying this material for, I think, solar cell applications, and they want to see how to increase the lifetime of the carrier in solar cells so that the collection efficiency becomes higher. So they found that in the high carrier density regime, the phonon bottleneck effect is found to increase the carrier lifetime significantly, 3 orders of magnitude. So this kind of mechanism, the phonon bottleneck effect, appears to be common under certain conditions, and the condition in our case is low temperature, very low temperature. So to find high operating temperature, the question is what can we do based on our findings. So this is one idea to demonstrate what we can do. So we can use quantum dot in a well structures. So the advantage of this structure is that the carriers will have long lifetime of quantum dots, and we can use the energy separation. We can easily change energy separation in quantum wells. So we can use these properties to develop a detector with this kind of mechanism. Carriers can be excited from the ground state to one of the quantum well label to form a quasi-equilibrium Fermi label there, and from that label infrared radiation can be detected. So to get a practical detector, let's look at some of the detectors that have been demonstrated already. This is quantum dot detector, p-type gallium arsenide, recently in our group. So there are transitions from ground state to different levels. So indium arsenide is quantum dot, and gallium arsenide is barrier. So there is barrier edge there. So the transition from ground state to close to the barrier gives this peak. And there's also another transition from ground state to the SO band, split up band, and which gives this peak around 2.2 micron. That is weak because this energy is not bound state like this. So if we make this state bound state, that will probably become a strong peak. However, 2.2 is not very useful because our interest is in 3 to 5 micron band. So to get to that, let's look at another device, quantum dot in a well. So similar quantum dots, but now it is in a well, 6 nanometer well. So there are additional energy labels, heavial 1, heavial 2, and again there is this barrier edge. So close to the barrier edge there is transition, and based on this transition the energy level is like the 0.23 electron volt, which is close to 5 micron, and there was that 5 micron, close to 5 micron peak absorbed. So there was this transition. So now what we can do from here is, now if we look at the difference between heavial 2 to the SO band. SO band is there, is not shown in this figure, but that will be there. So if we look at this difference, heavial 2 to SO band, the energy difference is 0.29 electron volt, which is corresponding to 4.3 micron wavelength. So if we get a peak at 4.3, this is kind of typical detector we are looking for 3 to 5 micron detection. So yes, so this device operated at 78 Kelvin or so liquid nitrogen temperature. However, now to make this state bound state, what we can do is we can use aluminum arsenide with high energy gap instead of gallium arsenide. So the barrier edge will go there. This SO band will be bound state. Whenever there is high energy barrier, now the darken will become much smaller because of the high energy barrier. So the operating temperature will go expectedly much higher than this temperature that can be expected. So this is dot in a well response. This is just dot, only dot. So this response is for this device, and this response is for this device. And these two are slightly different in the sense that the quantum dots are in a well now, so that there are additional energy levels. Dot energy levels and well energy levels, there are only dot energy levels. Yes. Yes, the thing is, so we are looking for a full width half maximum in the 3 to 5, in the 3 to 5 range. And for that one, peaks should be close to 4 micron. That is one thing. Another thing is operating temperature. So now it is like liquid nitrogen temperature. So the expectation with the new mechanism is that there will be high barrier, so that operating temperature will be also much higher. That is expected. That can be expected. Uh, Again, this is also 78K. Yeah. So mostly, yeah, we do the measurements at liquid nitrogen, and if the device is operating, we try to get higher operating temperature. But the so for this one, 3 micrometer. Um, yes, that is not clear here, but 3 micrometer, maybe somewhere around there. Oh yeah, this one didn't show. Probably only this peak was picked up to show for this one. Yeah, so 3 micron in this one is not there, but probably around 2.2, probably that was there, I guess. All right. Okay. Okay. Yeah, so right now it is not there, but what I'm saying is if we make those changes, proposed changes, we can expect to show 3 to 5. Okay, okay. Responsivity, rest. But they're basically the same. I think so. The first, yeah, the different people wrote paper and they chose their own way of writing the words. But I think basically same. Yeah. So yeah. So stronger actually than this one. Probably it was not done because I think at room temperature there was no response in this one. Probably for this one, 120, I guess. But this one, I think it was measured only at 78. Yes. So in the next, I'm going to show you the dark current characteristics. So we use a 3D model to fit the experimental dark current, uh, experimentally measured dark current area, electrically active area, not the optical. And this term P is the carrier thermally excited carrier density. V is velocity, which depends on the applied field, and the model becomes this, where this Fermi level is measured for p-type, measured with the valence band age as the reference 0, and that depends on the doping label and density of states, which is given by this, and also there is empirical uh, uh, relation for this term. And also for mobility, there is empirical relation that depends on mobility and temperature. Sorry, the doping density and the temperature. And saturation velocity is has also empirical relation, where A is not the area; it's just constant. Okay. And for gallium arsenide, the report value is around 0.6 or so. So the experimentally measured dark current. This is for the reference device without extended wavelength mechanism. This is the fitting, and these are the fitting parameters alpha. So we use delta value close to design for this device, which was 0.3 electron volt, and we obtain the fitting. In similar fashion, for the extended wavelength detector, also we use the delta value that was from the design, and we found this fitting. So the idea here is that even though the energy corresponding to the threshold of extended wavelength mechanism is much smaller, that means to a very long wavelength, the dark current is still controlled by that high heterostructure energy gap. It's not related to the small threshold, photoresponse threshold. So that is the advantage. And to give you an example, so the reference device and the extended wavelength device, these bias values have here same dark current values, but at the same biases, the photoresponse measured at 50K, so that the conventional device without the extended mechanism has close to 5.2 micron or so. However, with the extended wavelength mechanism, with the same dark current, that is longer, the spectra goes to longer wavelength. So to summarize, the mechanism of extended wavelength enables the infrared radiation detection beyond the limit, the limit of this conventional rule. And experimentally, it was found that a barrier offset is necessary, because without the barrier offset, we didn't see any extended wavelength photoresponse. And increasing the barrier offset, we saw increasing photoresponse, but with the gradient, it didn't change much. And we observed the extended wavelength mechanism even without a net carrier injection with the bias. we observe that result at 0 volt. So that means the quasi-Fermi level, quasi-equilibrium Fermi level appears to be in the same level from devices to devices. And also from the temperature dependence of the mechanism, we found that the hot phonon bottleneck effect is critical requirement for this mechanism. And based on this finding, we can see that if we use low dimensional structure, means quantum dots and quantum dot in a well like that, where there is energy confinement to have energy mismatch with the phonons, this we can expect that the operating temperature of these devices with the extended wavelength mechanism can be higher. We can get high operating temperature. And the dark current appears to be determined by the designed value of the heterostructure, not the delta corresponding to the extended photoresponse. Next, I'm going to show my continued work on split of band detector. These are from also from the work I presented in my MS defense. So we used a blocking barrier on a regular 30 period heterostructure with graded barrier to operate at 0 bias. This is the structure, heterostructure schematic, and there was middle contact, thick middle contact, and that was used to measure the response without the blocking barrier and with the blocking barrier on the same device to see the difference. And this is the processed MESA, top contact, middle contact, bottom contact. So the photoresponse with the current blocking barrier was slightly weaker compared without the current blocking barrier. However, the specific detectivity, D star, was much higher, about 2 orders of magnitude higher with the blocking barrier, and that operated at 0 bias because of the graded barrier. And with the application of bias, the photoresponse increased slightly in both cases. However, the specific detectivity decreased with the bias, because with the application of bias, the dark current increases significantly, and that causes the specific detectivity to go down with the applied bias. So that means with the graded barrier, with the 0 bias operation, the device appears to be the most optimized condition for the operation. Again, we are interested in higher temperature. So looking at the temperature effect from 77 K to 120 K, we see a significant reduction in the strength of the photoresponse, and that is up to 130 K, but after that, that photoresponse is mostly limited in the range of 2.5 micron or so, which is corresponding to the high energy blocking barrier. Now the rest of the device appears to be not active at high operating temperature. So we modified the original device. We removed that thick middle contact to make it narrow, about 20 nanometer, and we also increased the aluminum fraction in the barrier so that the barrier is slightly higher. The reason is we expect the device to operate at higher temperatures. So what we see here is we didn't see a drastic reduction in the photoresponse from 77 K to 120 K. Actually, it goes up slightly instead of going down. However, after 120 K, it again goes down, and we see the response up to 150 K in this one. So by comparison, original device and the modified device at 120 K, since there is no significant reduction in the photoresponse, the modified device shows higher photoresponse, and blocking barrier original device shows weaker. And the difference in the range of spectra is because of the increase in the aluminum fraction in this device, modified device. With increase in the aluminum fraction, energy barrier is now slightly higher, so the response threshold is slightly shorter. D star is also slightly higher in the modified device at 120 K. So now we saw that with increasing the aluminum fraction was one option. However, if we look at the spectra, the peak absorption is around 2.7 micron split up band, and by increasing this aluminum fraction, the response in 3 to 5 becomes actually weaker and weaker. So that is because the absorption property of the p-type gallium arsenide has absorption deep near 3.5 micron. That's the reason. So looking at the absorption of another material, p-type indium phosphide, actually has kind of peak in 3 to 5 range. So we are interested in this material system, and currently we have devices under production based on p-type indium phosphide. We have 3 devices, and we expect, based on the absorption properties, this is the simulated photoresponse, and we expect a 3 to 5 full with half maximum band based on this p-type indium phosphide. The device is currently under production. So now we have gallium arsenide, indium phosphide. So looking at the quaternary alloy of gallium indium arsenide phosphide, we see that we can tune that split of peak absorption from the wavelengths of like 3 micron to maybe 12 micron or so. So what we are doing is we are also expecting new samples based on this material system. The samples are under production, thin films are under production, and we also expect to be able to develop detectors where we can tune and choose the split of peak for 3 to 5 mid-infrared detection range. So these are the related publications related to extended wavelength and blocking barrier devices. I'd like to thank my advisor, Dr. Pereira, for all the support and guidance, and my committee members, Dr. Palkov, Dr. Damala, Dr. Gais, Dr. Kozanov, and Dr. Lee, and our collaborators at University of Leeds, UK, Dr. Linfield, Dr. Lee, Dr. Chain, and all my colleagues, funding agencies, US Army Research Office, National Science Foundation, BNV Fellowship from Neuroscience Institute, and dissertation grant from GSU, and all the faculty, especially Chair Dr. Lepine, Dr. Graduate Director Dr. Murad Sasser, and all the faculty and staff in the physics and astronomy. Thank you all for your attention. So from our collaborators, they do the growth and they also do the processing. Processing means first layer by layer growth using molecular beam epitaxy method, and then processing means getting those mesas and contacts using photolithography and metal evaporation, those methods. So they do both steps. First we give them the design, the parameters, and based on those parameters they do the growth and they do the processing and they send us to us, and after that I do the wire bonding and do the further characterization, photoresponse characterization, electrical characterization, and those steps. And yeah, but now the other devices under production currently are from companies because they don't have the growth system for indium phosphide. So the indium phosphide, the samples that this one, they don't have the capability for this system, so this is from a commercial company. And also this sample based on this idea are also from a private commercial company, because these are probably not easy for all growers, so we have to find specific places where they can do and they're willing to do the samples.